Right, so these are Chapter 17 review problems. They start, let me see if I can find the page number. This is in our e-text, page 443 of our e-text. All right, so these are the mathematical problems. First one says, how far away is the star Spica, whose parallax is 0.012? What would Spica's parallax be if it were measured for an observatory on Neptune's moon Triton, as Neptune orbits the sun? Okay, so that's part B. So for part A, it's really trivial. We're using this equation right here. Let me get to my mouse. Here's the equation. The distance is 1 over the parallax, and the parallax has to be in arc seconds. And so it's 1 over 0.012, and the 2 hash marks means arc seconds, and so that's equal to 83.3 parsecs. If you wanted to, it doesn't ask us to do that, but I just want to remind you guys you can do this. If we wanted to convert this from parsecs to light years, we know that in one light year, there is 3.26 parsecs. All right, and so you take that and you divide it, and that would give you the number of light years. Take 83.3 divided by 3.26, and that would give you light years, which I have not figured out. Let me get my calculator. So when I just did this, it turns out to be about 25.6 light years away. All right, so it doesn't ask us to do that. The answer is perfectly good if you leave it in parsecs. All right, so for part B, let's look at that again. It says if we're at an observatory on Neptune's moon Triton. So it turns out that Neptune has a distance of 30 parsecs. I'm sorry, of 30 astronomical units. All right, so Neptune, right? Neptune has basically its baseline. All right, so the baseline is equal to 30 astronomical units. Right, and so we got to actually look back at where did this equation really come from? It's using the Earth. So the one here is actually the fact that the Earth has one astronomical unit from the sun. All right, so here's what we can do. The distance to this star is going to be the same whether you look at it from the Earth or from Neptune's moon Triton, which is the largest moon of Neptune. Anyhow, so the distance is the same, and so here's what we can do. So the distance will equal, I'll do it this way, it's going to equal the baseline, right, the baseline, which I guess I should have put an L there, the baseline divided by the parallax. All right, and that's equal to, of course, the Earth's baseline is 1 divided by the parallax, which we know the parallax is 0.012, right? And of course, it's arc seconds. All right, so just with that information, I can take this and set it equal to this. All right, where the baseline is 30 astronomical units. All right, so here's what it looks like. 30 over the parallax from Triton is going to equal 1, which is of course the 1 astronomical unit divided by, as the parallax as seen from Earth would be 0.012. All right, and so really you just have one unknown in that equation, and that's the parallax, right? And so you just kind of do a little algebra with it. The p comes over to this to the left hand side. The 0.012 goes over to the right hand side, and so it becomes this. It's really simple. The parallax will equal 30 times 0.012, and of course that's arc seconds. And so the parallax as seen from Triton would turn out to be 0.36. 0.36, and of course it's still in arc seconds. All right, so quite a difference when you use. Of course, we don't have any telescopes on Triton, at least not currently. It would be nice if we could extend the baseline out this far, but we've extended the baseline out with the spacecraft Hipparchus, and also more recently the spacecraft Gaia. All right, let's do the next problem. All right, for number 2, it turns out that 1 arc second, remember these 2 hash marks mean 1 arc second, is the equivalent of 1 astronomical unit. So 1 arc second in the sky is, you're talking about a distance of 1 astronomical unit. And just as a reminder, 1 astronomical unit is the average distance between the Earth and the Sun. And so in kilometers, that's 1.5 times 10 to the 8th kilometers, or 150 million kilometers. All right, so there's a couple other terms that we need to talk about. The proper motion, it's usually given the symbol mu, that's the Greek letter mu, and the value that you're given is usually in arc seconds per year, all right? And then r is the distance in parsecs. And so the velocity, okay, so this is the important equation. The velocity, or let's see, what are they looking for? They're looking for the transverse velocity. So the transverse velocity, or also known as the tangential velocity, you can call it either one, but we'll use transverse velocity because that's what they're talking about, is equal to, it turns out it's going to equal mu times r, where r is the distance to that star or that object in parsecs. All right, so what is that? That's, basically you look, I'll draw a really crude picture here. So you look out into into space, and you want to know, you see the object here. Sometime later, usually many years later, the object is here with respect to the background of stars, right? And so that's what we call proper motion. And so the star has moved from here to here, and so it's undergone some angle per year, right? Some angle of arc seconds per year. And then if you know this distance, right, the distance to the star r, when you multiply the angle per year times the distance, and you got to convert the distance from parsecs to kilometers, of course. We do that here. So 1 arc second, again, as I started, 1 arc second of sky. So if you look out there and you see 1 arc second of sky, you know that this the distance that it's covered is 1 astronomical unit, right? All right, so let's read the problem. Number 2. It says a star lying 20 parsecs from the sun has a proper motion. All right, so we right away we know what r is, right? So r is 20 parsecs. 20 parsecs. And it has a proper motion of 0.5 arc seconds. It doesn't say that, but that's what it is. All right, so the proper motion, which is given the symbol mu, is 0.5 arc seconds, which I'll use the double hash, per year. All right, and so what is the star's transverse velocity? And then it says if the star's spectral lines observe a redshift to be 0.01%, calculate the magnitude of its 3-dimensional velocity relative to the sun. All right, so that's much more complicated. So what we're going to do is we're going to first figure out this transverse velocity. All right, and then what we'll do is we'll use the Pythagorean theorem to work out the transverse velocity and And we'll combine that with what's called the radial velocity. The radial velocity is the velocity towards us. You know, if this is us viewing the star. If we look, that's somebody's eye, supposedly, or a telescope. So if we combine these two, it's going to be some velocity in this direction, right? That's the true velocity. All right, so let's work on this part. All right, so we'll get the transverse velocity. All right, and so well, here we go. So the transverse velocity is equal to. So as I said up here, it's mu times r, so it's going to be 0.5 arc seconds per year times 20 parsecs. 20 parsecs. All right, and so this turns out to be 10 parsecs per year. Right, 10 parsecs per year. But we want to know what that is. The ultimate thing is to convert that to kilometers per second. All right, so that's really what we're looking for. Now this just becomes a conversion process. So you can kind of see that you can convert years to seconds, and then how do we convert parsecs to kilometers? All right, so remember one arc second is the equivalent of 1 arc second would be 1 parsec, and that is also 1 astronomical unit, right? So if there's 10 of them, we just multiply 1 arc, so that would be 10 arc seconds or 10 astronomical units that it's moved, or you multiply 10 by this number, and that would give us how much the star is moved. All right, let me read. All right, so this is where we left off. 10 parsecs per year for this particular star that's 20 parsecs away and moves with a proper motion of 0.5 arc seconds per year. All right, so anyhow, the way that we do this is it turns out, of course, that 1 parsec of sky would also be 1 astronomical unit, and so this would be 10 astronomical units. All right, so that's actually a really easy conversion. I don't really even have to write this down, but anyhow, 1 parsec is 1 AU. All right, so of course 10 parsecs would be 10 AU. That's AU. All right, so that those cancel. That's pretty trivial. That didn't really do anything for us. But the next step is really critical. So now I can convert 1 AU, right, to actual kilometers. So that's it turns out to be 1.5. That's a 5 times 10 to the 8th kilometers. All right. So that's fine, and so notice the astronomical units cancel. So you just multiply 10 times 1.5 times 10 to the 8th, and so that becomes 1.5 times 10 to the 9th, right? 1.5. Oh man, that doesn't look like a 5. Sorry. Let's erase that. Let's erase that right there. Sorry about that. 1.5. 1.5. That's supposed to be a decimal. And so that's going to be times 10 to the 9th kilometers. Okay, so we're getting close, per year. But then you can convert a year to seconds. That's actually pretty simple. I'll do that real quick. 1 year. So here's what we do. We know in 1 year there are 365 days. It's not exactly 365, so it's actually closer to 365.26. Just anyhow, and then so that's days, and then we know there are in 1 day there are 24 hours, and in 1 hour there are 60 minutes. Remember to use MIN for minutes to distinguish it from meters. And of course there's 60 seconds in 1 minute. all right, and so that cancels, the hours cancel, the days cancel, and the years cancel, all right, and so you multiply